Repeat this concept because, in my opinion, it is rather important. When you have a system, the micro length scale, the small length scale, and the big length scale, because you know micro, macro, you don't sound difference. So the small micro scale needs a mathematical model in which you have kinematical descriptors and, if you believe in Ehring and Truesdell viewpoint, different balance postulates. Then you, at macro level, other phenomena are relevant. So you have another list of kinematical descriptors, each having its own. Do you guess which is the balance laws which are micro level, which contribute to a certain balance macro level? This is a nightmare. It is very difficult without the a priori knowledge usually given by variational principles to understand which micro balance laws contribute to a certain macro balance law. So the idea, if you have an energy, the idea is simple. The total energy is the same, either if you represent it at micro level or if you represent it at macro level. And in this way, as the principle of virtual work is dealing with the variations of every kinematical field, you get what is needed for identifying macro and micro. Now, to go back to the principle of velocities, and we need how to formulate the part with powers by distance, points at which it is applied along the line of application of this same power will be equal to 0 if the small distances traveled in the same direction as the power are considered as positive and the distances traveled in the opposite direction as negative. This is the description of mathematical field. Of Lagrange, sorry, power in the meaning of mechanics, is a linear continuous function in the space of virtual displacement. If you want to show that you are well educated in mathematics, you can say that in the tangent bundle of the manifold which is describing your define in every point of this tangent bundle, remark that usually these are infinite dimensional spaces. So you have a Banach manifold or even a Fréchet manifold. And in this space, you need to define a linear continuous function because you expect that the inner product between the force or generalized forces with the virtual displacement is a linear. Now, I will come back. Distributions and Schwarz. And virtual displacements are test functions. Okay, so the idea is here in the works of Paul Germain is that at the end of the story, Lagrange statement can be reformulated even for founding continuum mechanics by using the abstract language of functional analysis and the theory of distribution. So the statement which we read about, written by Truesdell, who claims that Lagrangian mechanics is limited to point mechanics and rigid body mechanics, simply shows that he has misunderstood the true concept behind Lagrange principle. You know, these words he wrote can be easily adapted when you call power a distribution. And you can adapt the treatment, you can use the theory of distribution for developing continuum mechanics. Okay? We move, I want to specify a little bit better the homogenization as conceived by Gabriel Piola, because here the audience is made by also experts in mechanics, and I want to underline that there are some differences due to ignorance. The process of obtaining macro theories in a rigorous way, starting from micro theories, is complicated. And so in order to proceed, we use this heuristic procedure. You know, we have a beautiful way of telling in Latin, excusatio non petita, accusatio manifesta. I was excusing me at the beginning, so I was accusing myself. When I said that we do not know really, we can simply conjecture which are the continuum macro model which are good for a certain micro system. And for telling you that we are not so stupid, I showed you Archimedes' text where he is inviting us to conjecture somehow the result and then to propose to mathematicians the proof. Of course, Archimedes was capable to do all the job by himself, and this is rather rare in history of science. Okay, so how we formulate the conjectures? First, we choose the macroscopic descriptors of the macro model. Second step, we make, and here you have the big conjecture, you identify microscopic kinematical descriptors in terms of macroscopic ones. This is pure invention, okay? Because you have many micro configurations which correspond to one macro configuration. However, we believe to be clever enough to identify one micro which is representative enough of the whole set of micro corresponding to a certain macro. Then we identify macro work with micro functionals. And finally, we get the derivation of macroscopic equations into properties. This is written in a crystal clear way in the text by Gabriel Piola in 1848. I could say that, let me polemical. If I were American, I would say that I invented it. Okay? Sorry? But you're not. Luckily, thanks God. Okay, now we start with the first postulate. Okay, the powers expended by the action exerted on or exerted inside a subbody B of your continuous body are distributions in the sense of Schwarz concentrated on B. Please consider that these are technical words which have a meaning in the sense of the theory of distributions. For instance, a distribution is concentrated on a Borel set when test functions non-vanishing in this Borel set give you non-negative, non-zero values. But if you have a test function concentrated outside B, the value of the distribution is 0. Okay, so don't behave like philologists who change the meaning of words. It is clear We can use all the theorems of definitions which I was obliged to study of Schwarz, and all these theorems became relevant in continuum mechanics. Think slowly, this is simple but delicate. Every distribution having compact support kappa can be represented as the sum of a finite number of derivative measures or included in kappa. This is a beautiful structure theorem for distributions. So if you accept the previous postulate, you know how your virtual work functional is built. This is unbelievable. For, you know, the power of mathematics is unbelievable. But now you can make a definition. A distribution is said to have order smaller than or equal to kappa if one represents it as the sum of derivatives with order smaller than or equal to kappa of measures. So you say that a distribution is order kappa if kappa is the highest order derivative appearing in its structure. And very important for what every distribution having support included in a regular, remark regular, means C infinity without order. And manifold M can be uniquely decomposed as a finite sum of transversal derivatives of extension of distributions defined on M. So, capable to use this theorem, we are capable to discuss about the principle of virtual in modern. So, don't believe I'm schizophrenic. I am trying to show one step after the other to see how the idea of synthesis of materials must be developed. So, the idea at the basis of Piola homogenization requires the choice of two classes of macro and micro virtual work functionals defined on the set of micro or macro admissible virtual displacements. So, the choice of test functions. The equivalence class of micro deformations corresponding to each macro deformations. And this equivalence class is identified by one microfield, and the consequent identification of micro and macro work functionals on corresponding macro, micro, and macro deformations, which lead macro constitutive equations in terms of the relevant properties of micro models. Now, we give the internal work functional for a continuum. Okay, so we have a continuum and we say the parts of this continuum are interacting one with the other. So for every virtual displacement, we have the internal work done by these internal forces. If you have a rigid body, this is 0. If you have a deformable body, this functional is non-vanishing. Okay, now, which internal power functional? I'm using power and work equivalently, virtual displacement or virtual velocities are involved. Okay. You have a theorem by Schwarz. It is a linear continuous functional. It is a distribution. The shape, the structure of this continuum is given by the internal work function for this continuum is given by 8, where T lambda in general should be measures. Okay? Now, Vladimir was asking me which is how you place Trussdellian postulation in this framework. It is easy. N equal 1. He got a vision and he decided that the internal power functional is given by T0 V, T1 dot grad V, and that's it. Of course, T0 cannot exist because the internal work function is invariant under Galilean transformation, so you are left with T1 grad V. So is dealing with a particular case of the most general possible theory. By the way, I was joking, but Green and Rivlin worked in the United States, and they called T lambda lambda times contravariant tensors. So actually, also in the United States, you had two parties, but for a reason, the Truesdellian one was dominating, even if in Berkeley there was a strong resistance against his domination, let us say. Okay, now we have another problem. I have chosen a kind of internal work functional. So I have done what we can call a constitutive choice. Okay? So I decided to limit my attention to a certain class of deformable bodies. Those with n equal a certain value, different, eventually different from 1, greater than 1. Okay. Which are the externally applied interactions to this continuum? Think about this. Are you surprised if I tell you that a Euler fluid whose deformation energy depends only on its actual density cannot sustain shear external forces? Nobody is surprised, because you are accustomed to this statement. Okay? Now, what is happening? You have chosen deformation energy in a certain way, then the class of applicable external forces is limited. Okay? So, by the way, again, this is written exactly, this example is written in Piola's book. Now, if you have an internal functional, you must ask yourself which are the compatible, in the framework of the model, which are the compatible boundary conditions, externally applied forces, which are admissible. Okay? Truesdell decides that boundary conditions can be determined empirically, experimentally. Okay. They have a problem. Okay? So what we do? We perform, so given the internal work functional, now I will read, performing subsequent integration by parts on the domain boundary faces. Remark, the domain is not regular anymore, and on boundary edges and boundary wedges, which are the vertices of this polyhedron, and using the principle of virtual work, which tells that internal power is equal to external power for every subbody and for every virtual displacement, virtual velocity v, one gets the class of admissible external interaction possible for a given continuum. And again, answering to Vladimir, the novelty you have for external interactions. Look at the first addend. There is no pointer. Okay. Look at the first addend. You have FV, force per unit volume in the first here. Then you have, what is a force? It is the dual, this is the dual in the power functional of the velocity. Then you have integral on the boundary of B of F dot V. So this is a force, thanks. It is a force per unit, no. You have to switch on. on the side. Okay, so you have a force per unit surface, okay? Then, which is rather new, you get forces per unit line and forces concentrated on wedges, okay? So this is what we are familiar with. But you have also the dual in work functional of the transverse derivatives of the virtual velocity on the surface, on the edges, and on the wedges.
Do they have to be compatible somehow?
Sorry?
Do they have to be compatible somehow?
What it means, compatible? All of these F's can be represented in terms of T lambdas in a generalized Cauchy theorem. So these F's are coming, must be balanced by an expression coming from the internal power given by T lambdas. Okay. Of course, if you consider rigid motion V, you get for the translation balance of forces, and for the rotation balance of momentum of forces. But with deformative V's, you get other necessary conditions to equilibrium which are lost if you postulate only balance of force and balance of moment of forces. And again, this is clearly written by Piola in his book. What is astonishing is that Truesdell calls theorem of Piola the theorem which proves that in equilibrium you have a necessary condition of balance of forces and moment of forces, but he has not understood that it is only necessary. It is not sufficient for equilibrium. Okay? So it is clearly he was reading what he wanted to read, not what was written. Okay, so we can easily deduce the class of natural and essential boundary conditions leading to well-posed problems, which for mathematicians is essential. Boundary conditions cannot be induced experimentally. Okay? Now, let's go to a slide which I added for answering a question. The problem of synthesis is not new. The mathematical methods to be used must be similar to those already used for designing analog circuits. I am old enough, maybe here few people are have my age or greater than my age. We had to study the circuits which were analog to specific partial differential equations. Why? Because in absence of digital computers, in order to calculate solutions of partial differential equations, you needed to build an electric circuit governed by the same equations, and then the solution was obtained reading the voltage somewhere in your circuit. Okay, so in the theory of analog circuits, you have the equations, and you must find the physical system governed by this equation. So an old technique which is reviving because of new applications. This was a very serious theory, and there is a fundamental theorem. The fundamental theorem in the synthesis of analog computers tells you that let us call elementary circuital elements the resistances, the inductances, the capacitances, and the transformers. Then there is this beautiful theorem. For every quadratic Lagrangian and quadratic Hamilton-Rayleigh dissipation function, it is possible to find a graph, and for every branch of the graph, an elementary linear circuital element such that the obtained circuit is governed by the governing Lagrangian equations. There is an algorithm which allows you to build the search circuit. In another situation, I will show you some experimental measures which I did with my group. We obtained this Kirchhoff plate element analog circuit. Okay, you have an automatic procedure producing one. There are infinite circuits. Okay, so then one has the problem of finding the simplest one. Okay, but in this moment, one is enough in this context. Okay, so now what we have to do, we must find a minimal set of elementary substructures that allows for, via suitable interconnections, the work functional. With some results, I could not solve the whole problem, concerning virtual work functionals, which are the first variation of a second gradient deformation energy. So I could solve partially the problem of synthesis of second gradient deformation energies, and with Mario and Raffaele Esposito and Antonio Calcaterra, we have solved a small problem, but they are serious mathematicians with the theorems, everything. The synthesis of a one-dimensional n gradient beam bar in extension. So we have some preliminary results. Okay, so let's go. Again, excusatio non petita. Why I am obliged to tell you this? Because I am using, I will explain you, very often in my papers, this microstructure, which is a pantographic microstructure. Again, you are all young. I was obliged to copy the complex signature of my father for falsifying the justification in high school when I did not want to go there. I was running after a girl those times. So the pantograph is what? You move this point on the signature of your father, and this point is on the sheet of paper where you want the copied signature. So even copying the signature of your father can be very useful in your research. Okay? This microstructure has a very interesting peculiarity. If the blue and red pivots, which play a different role, are perfect, so rotations are allowed without any energy dissipation, okay, this elongation is with zero energy. Okay? We assume that the constituted beams are flexible and are interconnected with perfect pivots. The relevant length scales are 3, beam thickness, blue pivot distance, the product of the number of the cells times the blue pivot distance, which is this length. Okay? Now, why excusatio non petita? Because people tell that I got a fixation on these pantographic beams, you know, like a senile fixation. I am conjecturing that in order to synthesize every nth gradient continuum, this is one of the needed elementary structure. So it is like telling to a professor of theory of circuits he has a fixation with inductors. Okay? So this is just for answering before Okay, so the most basic substructure in the synthesis of second gradient materials is the pantographic beam. Somebody told me, okay, but these are beams. You must do with truss, only extensional bars. Look on the left and you have the same behavior. Okay, so just for telling you how life is running away, in 2003, with Jean-Jacques Alibert, Pierre Seppecher, we wrote this paper, Truss Modular Beams with Deformation Energy Depending on Higher Displacement Gradients. Okay? And after 20 years, I have done less than 1/3 of what I wanted to do in 5 years. The problem is the following. I have this energy, linearized energy. So you have this term, which is standard elastica, Euler elastica term, and this is the new second gradient term. U1 is the displacement in the axial direction. So this is the second gradient term. Okay. We have proven that this pantographic beam is the synthesis of this energy. And we have proven everything, also gamma convergence, everything. This is well established. Okay? A small commentary. Remark that in Italy we have two distinct disciplinary groups. So you cannot be professor of structural mechanics and mechanics applied to machines, because they are different. You know, we have, and also you cannot be professor of mathematical physics. This is crazy, because this is the elementary structure, a machine, which allows you to build a macro second gradient material. So, in the crazy subdivision of knowledge made by Italian legislator, you need two full professors for studying it, one discussing the microstructure and the other describing the macrostructure. Okay? By the way, in France, you have a unique group, the 60e mécanique, where you have everything. So this is one of the reasons for which I like France very much. Okay? Okay, now I start running because I want to show you that with some pain, using a microstructure made of springs. So you have extensional springs, rotational springs, and points. So with microstructure very simple, we could find the energy of this pantographic beam in nonlinear regimes. And together with the bending term, whose coefficients depends on elongation rho, you have a term which depends on rho prime. So the derivative along the configuration axis of the beam of the elongation. And then 8 years later, we have proven that if you have this microstructure, you can get a beam whose deformation energy is governed by third derivatives of transverse displacement. Okay, so we are beginning to build the iterative process for building any nth gradient continuum in this way. By the way, a last comment. What I'm doing? A last comment is needed. Truesdell decided that second gradient continua cannot exist because the second derivative is negligible in a Taylor expansion. So, in his opinion, the second gradient is always negligible with respect to the first gradient. Okay, this is a good argument, of course, but look, this microstructure has zero energy for elongations. Nothing is negligible compared with zero. So one should teach to Truesdell that a Taylor expansion has a dominant first term if the first term is non-vanishing. If the first derivative is zero, the second term is vanishing. Okay? And this was the crucial point in the argument we have used in this paper. Okay? Okay, now I must run. Of course, macro identification can give you an idea of how you can realize the boundary conditions which you have calculated at macro level. For instance, this beam here, this pantographic beam, if you want to block elongation, needs a double pivot there, and the double pivot is exerting a vincular reaction given by these micro forces. Now remark that this pair of forces exert non-vanishing power on a virtual displacement which is changing the length of the cell, okay? In the limit, this animal is expending power on the normal derivative, so on the derivative along this axis of the beam. So you have what is called reactive double force. That is not a couple. It expends work on elongations. Okay, then we wanted to have a plate, 2D plate, whose deformation energy depends on second gradient of in-plane displacement. Okay? The deformation energy which we conjectured was that, and then this is an incomplete second gradient energy. Some second order derivatives are not appearing in the energy. But, you know, one is moving one step after the other, okay? And the synthesis which we obtained is this structure. Here you have beams, and in every node you have a perfect pivot, and you can understand why you get second gradient contribution. This beam is bent, and therefore the second derivative of displacement of this beam gives you a contribution to the energy. There is a floppy mode without constraints, boundary condition, which is this one. This is a mode of zero order, of zero energy. Okay? Okay, then we wanted a more complicated energy with more second order derivatives, and we assembled pantographs horizontal with pantograph vertical, and then all these are zero energy deformations, and therefore what we will get is a pure second gradient energy without first terms in the Taylor expansion, as I said you. This is the micro structure made of springs. We also made a study of dynamic problems for that. And we found another mathematical problem. As the energies are incomplete, available theorems of existence and uniqueness are not applicable. Thanks God, Nikolsky, a Russian mathematician of the 50s, wrote many books about anisotropic Sobolev spaces, which are spaces in which the norm has only some derivatives of higher order, and therefore applying his theorems, of course boundary conditions must block floppy modes to get well-posedness results. So not only rigid motion, but also every floppy mode must be blocked by boundary conditions. We got a theorem which we published with Viktor Eremeyev, Claude Boutin, and David Stegman in Journal of Elasticity. Okay, now I will show you that everything is not a dream. We could print with 3D printers these microstructures. An important warning is needed. This has to be understood. This is wide knit pantograph. This is middle knit pantograph. This is a dense knit pantograph. We were expecting that the continuum model did not apply here. Miracle. It works perfectly also here. One should understand why. This is an important question. Okay, so is the idea of identifying micro with macro energy new? Green, Green, Saint-Venant, and Euler did exactly the same identification for the beam theory. And so we said already that. What is important is that Paul Germain was made a step in the progress of the scientific program established by Lagrange. And okay, look, I cannot resist to this, but I think that everybody knows that on ne trouvera point de figure dans cet ouvrage. In mécanique analytique, Lagrange claims that he can do everything with algebra without drawing anything. Okay. So what we did, we studied 3-point bending test for new pantographic structures. In standard theory, you have this deformation, this bending closes the bending in the opposite direction. So using a Greek term, Saint-Venant called anticlastic deformation of the transverse section. Okay, now, thanks God, I have a friend who printed this specimen, and I have another friend who, François Hilde at École Normale Supérieure Paris-Saclay. By the way, I must acknowledge my affiliation at l'École Normale Supérieure de Paris-Saclay for 3 years, starting from this one. This is not a numerical simulation. This is an experiment. In Paris, they have a tomograph. You place your specimen inside, and you can see inside it everything, producing these pictures. And this pantographic structure has non-anticlastic deformation of the lateral section. So this is an extremely exotic behavior. And now what is important, the deformation on the upper face is not transmitted to the bottom face, which remains nearly plane. Look, we are exploring the inside of this. By the way, the dark colors are density of the 3D printed object. So it is darker where it is denser. Now, this could be a wonderful shield. You have a deformation of the top and no deformation at the bottom. And the arch effect is producing this nice mechanical phenomenon. These are arches, okay? And now we are exploring it. I don't know why I cannot control the speed of this software, but you know, but at the end of this, you will see that we are cutting the specimen. You know, Cauchy imagined to cut a deformable body in 2 parts. These are the Cauchy cuts, and to study the action of the removed part on the remained part. Now this we can do in experiments. So you can measure everywhere the deformation. By the way, nobody is measuring forces. You measure only deformations. This is clear. Force measurements are obtained using a theory. You need something like Hooke or Law or a generalized one. Okay, we made in Berlin measurements in shear deformation of pantographic beams, and beautiful, look at this. A pantographic beam is experiencing a change of phase driven by deformation. It behaves as a Euler beam in the first part of the deformation process and as a cable in the second part of the process. And then we printed bipantographic sheets. These are all the details of, this is a deformation of this bipantographic beam. And we also built the boundary conditions when we printed it. So we imposed that the normal derivative is 0. Okay? And we also, using multi-photon lithography, we constructed pantographic microfabrics. This is 20 micrometers. Okay? And we built a device for elongating this with a micro device. And we printed a millimetric microarchitecture, and we studied this module for getting the information of the behavior of the big structure. In this paper by Anil Misra, is the leader of this group, we have found that the dimension of this small pivot here is critical for the macro behavior of the structure. So we have proven that you can double the force, no, 5 times the force can be exerted by the same microarchitecture if you simply change this pivot. Changing 1% of the volume of the specimen, you can have 5 times more the force, which is another really exotic behavior. Okay, then I printed it with metal. You know, this is a multifocal picture which I've shot myself. And this is the perfect pivot realization using 3D printing in one shot. So you can have perfect pivots printed like that. And again, we have an evidence against inductivism. Okay? What we did with Franz Wild. You know, let me say a word for French education system. I hope that they will not change it. You have like Grande École, and even if maybe they are decadent, they are complaining, but they are producing outstanding people. And in Italy, we soon lose the contact with French science because we don't have something like that. Franz Wild is an experimentalist. He is dressing the white jacket of the man entering in the lab. However, he knows very well epistemology and variational principles. Okay. Now, what I asked him to measure with digital image correlation this deformation. He did not manage with standard algorithms. Then, why? Because in large deformation, it is very difficult to recognize where a material subbody individuated in the reference configuration is placed in the present configuration. This is a technical problem, very serious. What Francois did, he used second gradient macro theories in the first row, or first gradient micro theory, second row, and predicted where each subbody should be placed. So he knows that the theory is driving the experiment. Okay? Then he developed a code which is looking for this subbody in the image obtained experimentally, having also taken into account the predicted change of shape. Okay? And the theory suggests where to find what we are looking for. So once more, the theory is necessary to make measurements. This measurement is impossible without being driven by the theory. Okay, so different fine elements and meshes are used in order to drive the digital image correlation with different models. So you have a code. The code is calculating theoretically the shape. This code is looking for, around this configuration, the image to verify that your theory is not falsified. Okay? Okay, I conclude showing you that I deposited too many years ago, in 1998, a patent in the United States for a first multi-physics metamaterial, which we called piezoelectromechanical plate. It has a piezoelectromechanical microarchitecture. You have a plate, piezoelectric transducers, and an electric circuit. So a structural element is connected via a distributed array of piezoelectric transducers to a suitably optimized electric circuit. Okay? And here we needed, for instance, to find the electric analog of a Timoshenko beam element. And for a beam, we made some simulations. This is the resonance of, I don't know why it is stopping, a resonance between electric and mechanical phenomena, and the colors are the charges which are traveling in the electric waveguide. Here you have the bending, here it is damped with an optimal damping. We added some resistors inside, and the same has been done. This is the first resonance of the first mode. This isovolt. This is the second mode. This is the coupling. This is the coupling. Okay. Being in a hurry is not good. This is the coupling after a hammer strike. But what is interesting is that with the same unique dissipative circuit, you can damp first mode, second mode, every mode up to the 9th. Okay, why not the 10th? Because the wavelength of the modal shape at the 10th modal shape is smaller than the piezoelectric actuator, so you cannot reach it. Okay, so conclusions. There is a unique model describing everything. Forget it. Different scales, different models. If you are at the length scale of 5 millimeters, you need a second gradient continuum for modeling this system. If your length scale is 1 millimeter, you need Euler beam theory. If you are at the length scale of 100 micrometers, Cauchy first gradient isotropic model is suitable. If you are at 10 micrometers, you need an isotropic Cauchy model. If you go lower, you need quantum mechanics, probably. And variational principles allow science to unveil nature. One of the most beautiful things in Paris, I think, is le Musée d'Orsay. And I think that only dans la Ville Lumière you can find a statue which was at the entrance of a faculty of science in the province. I forgot where. It could be Toulouse. La nature se dévoilant à la science. Okay, so you have this beautiful lady, and if you talk to her with the right language, she shows you her beauty. And I suggest you use variational principles, otherwise she will be very shy. Thanks a lot.